IFR training video, by
Toga thrust.
ADF. ADF tracking. Agenda. Introduction. System description. Tracking radials. Failures and contingencies. QDM, QDR.
Introduction.
We are facing major changes in aviation, mainly in instrument flying. With the growing importance of satellite positioning, old-fashioned navigation and approach techniques will soon become obsolete. What about pilot core competencies? Are we bound to follow the line and nothing more, or should we keep training those procedures and techniques to keep what makes a pilot, mastering? You think right if you are watching this video. Let's train as a pilot. Satellite navigation and approach techniques will be a part of your training.
Theory.
System description. The non-directional radio beacon, NDB, is a low or medium frequency radio beacon that transmits non-directional signals, whereby the pilot of an aircraft properly equipped can determine bearings and home to the station. The pilot, through the use of an automatic direction finder, uses these signals in order to determine relative, magnetic bearing and therefore position. The entire system consists of ground station, ADF receiver, antenna, loop antenna, magnetic bearing from the airplane to the station, sense antenna, directional information. Now, both antennas are combined into one single element. Bearing indicator. These facilities normally operate in a frequency band of 190 to 535 kHz. According to International Civil Aviation Organization, ICAO, Annex 10, the frequency range for NDBs is between 190 and 1750 kHz, and transmit a continuous carrier with either 400 or 1020 Hz modulation. The NDB frequency can sometimes bleed over to the AM radio frequency band, and likewise radios can bleed over onto the NDB frequency. On aeronautical charts, NDB are represented with this logo. All radio beacons except the compass locators transmit a continuous 3-letter identification in code except during voice transmissions. NDB frequency and identification information is found on aeronautical charts. The Morse codes are used to identify the NDB stations, while the commercial broadcast stations are identified at random times by the station's announcer. These signals can be used to either home or intercept and track a course for navigation. Advantages. Relatively simple and low cost. Accuracy is suitable for navigation but subject to numerous limitations. Not limited by line of sight, which permits reception at low altitudes over great distances due to ground waves. Automatic direction finder receivers may be composed of fixed compass card. You must calculate the bearing from your actual heading. Movable, rotating, compass card. You turn the knob to set your actual heading and read the bearing on the needle. Slaved movable compass card. The card is linked to your actual heading automatically, no knob to turn. Single needled radio magnetic indicator, RMI. Dual needle radio magnetic indicator, RMI, one single yellow and one double green to avoid misreadings. Fixed compass card. A fixed compass card simply means the face of the instrument cannot rotate, leaving only the needles to move. Always represent the nose of the aircraft at 0 degrees and the tail as 180 degrees. Visualizing the situation with this type of indicator can be daunting. Relative bearing, plus, magnetic heading, equals, magnetic bearing. Relative bearing RB are the degrees flown to station, clockwise. Magnetic bearing, degrees from magnetic north. Movable compass card. Pilot can rotate the face of the card. The ADF needle will directly indicate the magnetic bearing to the NDB when the aircraft heading is shown at the top. Here, magnetic bearing to the station is 300 degrees. Dual needle radiomagnetic indicator. Has a second needle. Both needle may be selected as ADF or VOR station. NDB applications. Navigation, from beacon to beacon. Intercepting and tracking, intercept and track a particular radial. Holding, enter a waiting pattern by flying depicted circuits. Instrument approaches, NDB approach. Homing, follow the head of the needle without any wind correction. Tracking, stay centered on a particular radial correcting for the wind. Non-directional beacon limitations. Radio beacons are subject to disturbances that may result in erroneous bearing information. Such disturbances result from factors such as lightning, precipitation, static, etc. Nearly all disturbances which affect the automatic direction finder, ADF, bearing, also affect the facility's identification. Noisy identification usually occurs when the ADF needle is erratic. Voice, music or erroneous identification may be heard when a steady false bearing is being displayed. Since ADF receivers do not have a flag to warn the pilot when erroneous bearing information is being displayed, the pilot should confirm the NDB's identification. If the reception is out, the needle should either freeze, or go to park condition, 90 degrees indication. Twilight error, night effect. Radio waves can be reflected back by the ionosphere and can cause fluctuations 30 to 60 nautical miles, approximately 54 to 108 kilometers. From the transmitter, especially just before sunrise and just after sunset. Terrain error. High terrain like hills and mountains can reflect radio waves, giving erroneous readings especially if they contain magnetic deposits. Electrical error. Electrical storms, and sometimes also electrical interference can cause the ADF needle to deflect toward the electrical source. Shoreline error. Low-frequency radio waves will refract or bend near a shoreline, especially if they are close, to parallel, to the shore. Bank error. When the aircraft is banked, the needle reading will be offset. Quadrantal error. Signal polluted by reflection on the aircraft's body. Twilight error, night effect. UVs and X-rays from the sun create layers of ionized atoms in high atmosphere. Some of these layers have refractive properties, and one acts as a wall preventing waves from the ground to reach the refractive particles. The night effect is the casual result of a favorable timing. There is a window after sunset where the blocking layer disappears, and the refracting particles are still active, albeit less active than on daytime. Ionosphere activity changes at sunset. Attenuated waves are redirected towards the ground during this period, possibly to a receiver located further than the horizon. In this phenomenon, ionized particles play the same role than hot air for looming. Terrain error. Over mountainous regions and sandy deserts, range of NDB signal is relatively lesser than that over the sea. Reliable range from an NDB located at shore may vary in directions. Reflection and diffraction of the radio waves in mountainous areas, mixed with ground wave, may cause fluctuations in signal. The bearings indicated may be in error, or change rapidly over such regions. Use of higher frequency in such cases may reduce the problem. Electrical error. Considerable electrical disturbance is created by thunderstorms, for attenuated NDB signals, at long ranges. Lightning from the thunderstorms produces strong signals and cause the ADF pointer to swing from direction of NDB towards electrical storm. Totally incorrect indications may be obtained during such adverse weather conditions. Shoreline error. Radio waves passing the coastline at small angles suffer refraction due to different conducting and reflecting properties over land and sea. A false bearing indication is obtained at aircraft flying over sea and taking bearings from NDB located over land. The effect is less for an NDB on coast than one inland and on a bearing 90 degrees to coastline than at an oblique angle. Hence, given the choice, use beacon at coast and rely on bearings perpendicular to the coastline. Bank error or dip error. To make things simpler, the needle will lie to you. End of the needle will move towards the low wing in a turn, making impossible an analysis of the magnetic bearing, until the wings are back to level. Then the needle will slowly come back to the correct reading. You can anticipate the correction for your rollout by considering an error of about 10 to 15 degrees. Quadrantal error. NDB signals may reach the receiver aerial directly, and also after being reflected by the aircraft body. Due to electrical circuits and current flowing through them, there is an electromagnetic field surrounding the aircraft, in general alignment with its body. This causes the incident radio waves to deflect near the ADF receiver aerial. The mixed signal affects the null position and the bearing indicated may be with large error. The maximum effect is at quadrantal relative bearings 045, 135, 225 and 315 relative to heading. Modern installations are compensated for this error. ADF navigation. Many airplanes are equipped with ADF radios which operate in the low and medium frequency bands. By tuning to low frequency, LF, radio stations such as NDBs, or to commercial broadcast, AM, stations, a pilot may use ADF for navigation in cross-country flying. Some major commercial broadcast station locations and frequencies are shown on sectional aeronautical charts. Most ADF radio receivers' signals are in the frequency spectrum of 190 kHz to 1750 kHz, which includes LF and MF navigation facilities, and the AM commercial broadcast stations. The ADF has automatic direction-seeking qualities which result in the bearing indicator always pointing to the station to which it is tuned. That is, when the bearing pointer is on the nose position, the station is directly ahead of the airplane. When the pointer is on the tail position, the station is directly behind the airplane, and when the pointer is 90 degrees to either side, wingtip position, the station is directly off the respective wingtip. The easiest, and perhaps the most common method of using ADF, is to home to the station. Since the ADF pointer always points to the station, the pilot can simply head the airplane so that the pointer is on the 0 degrees or nose position. The station, then, will be directly ahead of the airplane. With a crosswind, however, the airplane would continually drift to the side and, unless a corrective change in heading is made, would no longer be flying straight to the station. This would be indicated by the pointer moving to the upwind side of the nose position on the dial. By periodically turning the airplane into the wind, toward the head of the pointer, so as to continually return the pointer to the 0 degrees position, the airplane can be flown to the station, although in a curving flight path as a result of wind drift. The lighter the crosswind and the shorter the distance from the station, the less the flight path curves. Upon arrival at and passing the station, the pointer will swing 180 degrees from a nose position to a tail position. One of the several valuable uses of ADF is the determination of the airplane's position along the course being flown. With 2 NDB station, you can obtain 2 radials. Plotting those 2 radials on a navigation chart will give you your actual position. NDB bearing tracking. When necessary to follow a course directly to or from an NDB while making necessary corrections for wind. After the course has been intercepted, maintain the heading that corresponds to the course to or bearing from the station. If a 10 degrees course deviation is indicated, off the nose or tail relative to the needle, then re-intercept by beginning with a change toward the head of the needle that is 20 degrees. Maintain the intercept heading until the angle of deflection from the nose or tail is 20 degrees and then turn to a new course heading by taking out half of the intercept angle. This new heading is the new relative bearing. If the ADF needle deflects toward the nose or away from the tail, re-intercept by beginning with a 10 degrees change in heading, intercept heading, toward the needle deflection. Maintain the intercept heading until the deflection angle equals the intercept angle, deflection equals correction, and then turn back to a new course heading by taking out half of the heading change. Note that larger correction angles can be used if the wind requires.
Tracking radials.
The way to get started is to quit talking and begin doing.
No wind correction, dogleg. Heading to the station, you just pick up the heading corresponding to the magnetic bearing to the station, QDM. For example, the picture here under with a QDM of 171 degrees, we then take a heading of 171 degrees, which is perfect in a no-wind condition. But if there is a crosswind component, the wind will push the aircraft away from its original QDM and the aircraft will fly a dogleg to the station, which is not the goal of the navigation. Let's visualize the problem in a short video. As you can see, we start the tracking with a QDM 170 degrees, but we have a crosswind of about 23 knots and we apply no correction for that wind. Progressively, the needle of the ADF is moving as the aircraft is drifting away due to the crosswind. We follow the needle, but still not applying any wind correction. The needle still moves and we follow it with the heading. The closer we are to the station, the faster the needle drifts away. Finally, we overfly the station, yes, but with a heading of 110 degrees, so 60 degrees away of our original heading to the station. We have just flown a dogleg. That's, of course, not the way to track a radial. With wind correction, tracking. Heading to the station, you just pick up the heading corresponding to the magnetic bearing to the station, QDM. For example, the picture here under with a QDM of 171 degrees, we then take a heading of 171 degrees, which is perfect in a no wind condition. But now, we take the wind into account and we apply a wind correction to stay on our QDM of 171 degrees. What correction should we apply? Airspeed number is equal to the cos divided by 60. In our case, ASN is equal to 141 divided by 60 equals 2.35. So the correction to apply is equal to the crosswind component, 23 knots, divided by the ASN, 2.35, equals plus or minus 10 degrees, 9.8 degrees. Let's then apply a 10 degrees correction against the crosswind. Crosswind is from the left, so take a correction to the left of 10 degrees. 171 degree minus 10 degrees equals 161 degree. Let's visualize the solution in a short video. Now, we apply a wind drift correction of 10 degrees against the crosswind component as computed previously. With that new heading, we will be able to stay on the radial 171 degree all along until passing overhead the station. Some small adjustments of 1 or 2 degrees are maybe necessary to have the maximum precision. And we overfly perfectly the station.
Failures, irregularities and contingencies.
The NDB being the most basic means of navigation existing, it is also in the process of being decommissioned. It is difficult to prepare a downgrade. In the event of a system failure, the only solution from an approach or navigation point of view is to upgrade to a more precise means of navigation, VOR, GPS. It should be noted that, in the event of a breakdown, no warning flag will be in sight of the pilot. The ADF needle can be placed in the parking position, an indication of 90 degrees of relative bearing, whatever the heading of the aircraft. Some instructors advocate listening to the NDB identification throughout its use, but this is not mandatory from an EASA regulations perspective. QDM, QDR. To complete this module, let's study the difference between a QDM and a QDR. Definition of a QDM, magnetic bearing to the station. Definition of a QDR, magnetic bearing from the station. On this picture, we see that, under no wind condition, our magnetic route to the beacon is 171 degree. The QDM is 171 degree and we are on the radial 351 degree from the station. So the QDR, magnetic bearing from the station is 351 degree as we are on the radial 351 degree from the station. Some exercises. Head of the needle, 304 degrees. So the QDM is 304 degrees and we are on the radial 124 degrees from the station. So the actual QDR is 124 degrees. Tail of the needle, 271 degree, so the QDR is 271 degrees and we are on the radial 271 degree from the station. So the actual QDM is 091 degree. Tail of the needle, 249 degrees, so the QDR is 249 degrees and we are on the radial 249 degrees from the station. So the actual QDM is 069 degrees. Of course, you have to keep in mind that, if you turn towards the station, the radius of turn will put your aircraft on a close but different radial than the one you were on at the start of the turn. Here, the QDM is 069 degrees and we turn towards the station. As we are very close to the station, the needle is moving fast and we finish the turn on a QDM 054 degrees.